For most of human history, we did not know whether planets existed beyond our sun. The night sky looked vast and silent. As recently as the early 1990s, we had not confirmed a single world orbiting another star. Now we know there are thousands, and likely billions more. Some are similar in size to Earth. Some orbit stars much like our own. Many circle within what astronomers call the habitable zone, the distance where liquid water could exist. Water matters. On Earth, wherever liquid water exists, life tends to follow. But distance alone guarantees nothing. Venus may once have been temperate before becoming hostile. Mars may once have had rivers before losing much of its atmosphere. Habitability is not a promise, it is a balance. We cannot see the surfaces of these distant planets. We detect them indirectly through faint dips of starlight or tiny stellar movements. Yet from that limited light, we estimate size, orbit, density, and sometimes even hints of atmosphere. In one nearby system, 7 Earth-sized planets orbit a small red star. At least 3 lie in the zone where water could exist. They are real, they are measurable, but they remain distant. Which leaves us with the deeper question: how close have we come to finding a world that truly resembles Earth? What would count as proof? And if such a planet exists, how would we even recognize it? Tonight, we step carefully among the most promising worlds discovered so far, guided only by what light has revealed. Before we begin, I'd love to know, where in the world are you listening tonight? Drop a comment and tell me what time it is where you're winding down. And if these gentle stories help you drift off, please tap like and consider subscribing. It keeps this little snoozy corner alive and cozy, and it means so much to have you here. So now take a deep breath, let your shoulders loosen, and let's begin with the worlds that almost seem possible. A single measure often guides the search, a quiet boundary drawn around distant stars. Astronomers call it the habitable zone, a region where temperatures might allow liquid water to remain stable on a planet's surface. It is not a visible ring nor a guarantee of comfort, but a calculation shaped by light and distance. Too close to a star, and heat drives water into vapor that escapes to space. Too far away, and cold locks it into endless ice. Between those extremes lies a narrow balance, defined by energy rather than appearance. Distance matters because stars pour out power unevenly. A bright, hot star casts its habitable zone farther outward, while a smaller red dwarf keeps its temperate region tucked close. Planets shift through this invisible band with precise consequences. A modest change in orbit can thicken clouds, thin oceans, or transform chemistry across an entire world. The placement must align not only with warmth but with time, since stars brighten as they age and gradually push that temperate boundary outward. Liquid water remains central because it acts as both solvent and stage. On Earth, chemistry unfolds within it. Molecules dissolve, collide, recombine. Cells depend on its ability to carry nutrients and regulate temperature. Wherever rivers flow or oceans pool, reactions sustain complexity. Yet the presence of water depends on more than sunlight. A planet requires an atmosphere capable of holding warmth without trapping too much. It must possess enough gravity to prevent precious gases from drifting away. The thickness of that envelope shapes pressure at the surface and determines whether water rests as liquid or escapes as vapor. The inner worlds of our own system illustrate how delicate this balance can be. Venus once may have held oceans beneath gentler skies, positioned within a zone similar to Earth's current orbit. Over time, greenhouse gases accumulated, heat intensified, and any surface water vanished into a dense, crushing atmosphere. Mars, slightly farther out, once carried rivers that etched valleys across its plains. As its interior cooled and its magnetic field weakened, much of its air was stripped away. Without sufficient pressure, water could no longer persist on the surface, leaving behind a cold and arid terrain. Magnetic fields play a quiet role in this story. Generated by churning interiors, they deflect charged particles from stellar winds that might otherwise erode atmospheres, molecule by molecule. Planetary mass shapes that interior vigor. A body too small cools quickly and loses protection, while one too large may gather thick blankets of gas, unlike anything breathable. For these reasons, habitability is not a simple label. It is a gradient shaped by distance, chemistry, gravity, and time. A planet may sit within the correct orbit, yet lack air, or hold air, yet possess no magnetic shield. The word suggests potential, measured not by comfort, but by conditions that allow water to remain steady and reactions to endure. In that quiet definition, possibility finds its most careful meaning. Long before any image of a distant world could be imagined, the discovery begins with patience and measurement. Stars are watched for months, sometimes years, their light recorded point by point, until subtle patterns begin to emerge. Within those steady beams, astronomers search for interruptions so slight they would vanish without careful attention. One method relies on alignment. When a planet passes between its star and our vantage point, it blocks a fraction of that starlight. The dimming is small, often less than a single percent, yet it repeats at regular intervals. These periodic fades form a light curve, a delicate graph of brightness over time. The depth of each dip reveals the planet's size relative to its star, while the spacing between dips traces the length of its orbit. From that rhythm alone, distance and temperature estimates can be drawn. The world itself remains unseen, but its passage leaves a signature in light. Another technique listens for motion rather than shadow. Planets do not simply orbit their stars, they pull on them as well. As a planet circles, the star responds with a slight wobble, moving toward and away from us in a slow, steady dance. This motion shifts the star's spectrum by tiny amounts, stretching and compressing wavelengths in a pattern known as radial velocity. By measuring those changes, astronomers infer the planet's mass and the strength of its gravitational influence. Together, these two methods reveal size, orbit, and density without ever resolving a surface. The transformation began in earnest with the launch of the Kepler Space Telescope. Positioned beyond Earth's atmosphere, it monitored more than 100,000 stars at once, searching for repeated dips in brightness. Thousands of candidate planets emerged from that patient survey, reshaping the sense of how common planetary systems might be. Later, the TESS mission widened the search, scanning nearly the entire sky and focusing on stars closer to home. Each dataset added new points of light to a growing map of unseen worlds. Most of the planets found so far are larger than Earth. Their size makes them easier to detect, since a bigger body blocks more starlight and exerts a stronger gravitational tug. Small rocky planets create fainter signals, often buried in stellar noise or masked by activity on the star's surface. Detecting them requires precision that presses against the limits of current instruments. Even when a planet appears similar in size to Earth and lies within a temperate orbit, uncertainties remain. Atmospheric composition, surface conditions, and magnetic shielding cannot be fully resolved from these distant measurements. In this way, the search advances through inference rather than sight. Light curves and spectral shifts stand in for landscapes and horizons. Each discovery is assembled from fragments of brightness and motion, forming a portrait that is precise yet incomplete. Within those quiet signals, entire worlds make their presence known, not by appearance, but by the careful mathematics of light and gravity. In the constellation Aquarius, a faint red ember glows with less than a tenth of the sun's mass. its light so subdued that it would be invisible to the unaided eye. Around this small, cool star moves a compact procession of 7 worlds, each close enough that their years pass in mere days. This system, known as TRAPPIST 1, reshaped the study of potentially habitable planets not through brightness, but through number and arrangement. All 7 planets are comparable in size to Earth, clustered so tightly that their orbits would fit well within the distance between Mercury and our Sun. 3 of them lie within the star's temperate region, where surface conditions might allow liquid water if atmospheres cooperate. Their proximity creates a striking geometry, neighboring planets looming large in one another's skies, gravitationally linked in subtle resonance that keeps their paths stable and predictable. Yet the star at their center is an ultra-cool red dwarf, smaller and dimmer than the Sun, radiating primarily in infrared light. Because its habitable zone rests so near, these planets circle at distances far closer than Mercury does to our own star. Such intimacy likely results in tidal locking, a state in which one hemisphere continually faces the star, while the other remains in perpetual darkness. Climate models suggest that a sufficiently thick atmosphere could distribute heat across this divide, softening temperature extremes and preventing atmospheric collapse on the night side. Without such circulation, stark contrasts would define the surface. Red dwarfs are long-lived and abundant, comprising the majority of stars in our galaxy. Their stability over trillions of years offers extended windows for planetary evolution. At the same time, they are prone to powerful flares, sudden bursts of radiation capable of stripping atmospheres and bathing nearby worlds in charged particles. For planets orbiting so close, magnetic shielding and atmospheric retention become critical defenses. The balance between stellar longevity and stellar volatility shapes the promise and peril of these systems. Among the 7, TRAPPIST 1e has drawn particular interest. Its radius and density indicate a rocky composition similar to Earth's, suggesting a solid surface rather than a deep envelope of gas. It receives an amount of stellar energy comparable to that of our planet, placing it near the center of the temperate band. Early observations from the James Webb Space Telescope have begun to probe the atmospheres of several planets in the system, searching for carbon dioxide, water vapor, and signs of thick, enveloping skies. Some results hint that certain inner planets lack substantial atmospheres, while others remain uncertain, their spectral fingerprints still faint. The TRAPPIST 1 system embodies the dual nature of red dwarf worlds. It presents multiple Earth-sized bodies in measurable orbits, close enough to study in detail, yet bound to a star whose behavior may test the resilience of any atmosphere that forms. In this quiet cluster, hope and hazard share the same narrow space, circling a star that glows softly but commands profound influence over the fate of its planets. Among the 7 closely bound planets in the TRAPPIST 1 system, one settles into a position that draws particular attention. It neither clings too near the faint red star nor drifts toward the colder edge of its gravitational family. TRAPPIST 1e moves within a band of starlight that resembles, in careful proportion, the energy Earth receives from the Sun. Its orbit completes in just over 6 days, yet within that brief circuit lies a balance measured not in duration but in warmth. In size, TRAPPIST 1e nearly mirrors Earth. Its radius is only slightly smaller, and measurements of its density suggest a composition rich in rock and metal rather than gas. This internal structure hints at a solid surface, a crust that could bear oceans or continents if other conditions align. From transit data and gravitational calculations, Astronomers estimate that its mass provides sufficient gravity to hold an atmosphere, should one exist. That retention is critical, since air governs temperature and pressure, determining whether water can remain liquid rather than evaporate or freeze. Because the planet orbits so close to its ultra-cool star, tidal forces likely have slowed its rotation until one hemisphere continually faces the light while the opposite side remains turned away. In such a configuration, the day side could receive steady illumination while the night side rests in prolonged darkness. Early climate models explore how heat might circulate between these extremes. If the atmosphere were thin, the contrast could be severe, with one hemisphere heated and the other locked in cold. Yet simulations indicate that a dense envelope of gases might transport warmth efficiently, smoothing the gradient and creating a ring of moderate conditions between perpetual day and unending night. The chemistry of that atmosphere remains uncertain. Observations with advanced telescopes have searched for molecular signatures in the faint glow that filters through as the planet crosses its star. So far, the signals are subtle and incomplete, leaving open the possibility of carbon dioxide, water vapor, or other common compounds. The absence of a thick hydrogen blanket suggests that TRAPPIST 1e is unlikely to resemble a miniature Neptune, strengthening the case for a rocky world with conditions not entirely foreign to terrestrial experience. Stellar activity still casts influence over its prospects. Red dwarfs can flare, releasing bursts of radiation capable of eroding atmospheric layers over time. The resilience of TRAPPIST 1e would depend on protective mechanisms, perhaps a magnetic field generated by an active core. Such shielding could deflect charged particles, preserving the gases needed for climate stability. In its modest orbit around a quiet ember of a star, TRAPPIST 1e embodies a careful intersection of factors: size, composition, distance, and potential atmosphere. None alone determines suitability for life. Together, they outline a world that approaches familiar parameters without fully revealing its surface. Within that narrow zone of equilibrium, possibility takes on a measured and tangible form, shaped by gravity, light, and the slow dynamics of planetary balance. Not far beyond the bright stars that anchor our southern sky, a dim red point moves quietly through space as part of a three-star family. This faint ember, Proxima Centauri, is the closest stellar neighbor to our Sun, separated from Earth by 4.2 light-years. In cosmic terms, that distance is modest. In human terms, it remains immense. Around this small red dwarf circles a planet with a mass comparable to Earth's, a world known as Proxima Centauri b. Its orbit lies within the narrow region, where temperatures could allow liquid water to exist, depending on the character of its atmosphere. The star it circles is far cooler and dimmer than the Sun, so the planet must travel close to receive adequate warmth. A single year there lasts just 11 Earth days, placing it in tight proximity to a star that glows softly but behaves unpredictably. Like many red dwarfs, Proxima Centauri releases powerful flares, bursts of radiation that can outshine the star's usual output in moments. Such activity carries energy capable of altering atmospheric chemistry or gradually eroding it altogether. Because the planet orbits so near, tidal forces likely have slowed its rotation into a locked state. One hemisphere may remain turned toward the star, bathed in continuous daylight, while the opposite side rests in prolonged darkness. Climate simulations explore whether winds and atmospheric currents could transport heat across this divide. If the atmosphere is sufficiently thick, warmth might circulate and temper the contrast. If it is thin or absent, the day side could grow intensely heated while the night side cools dramatically. Much depends on properties that remain unseen. The planet's mass suggests a rocky composition, and its gravity appears strong enough to retain gases if they are present. Yet the history of its star introduces uncertainty. Frequent flares in Proxima Centauri's early years may have stripped away lighter elements, leaving the surface exposed or reshaped over time. Whether a magnetic field exists to provide shielding is unknown, and such protection would influence how well an atmosphere could endure. Despite being our nearest candidate beyond the solar system, Proxima Centauri b remains unreachable with present technology. Light itself requires 4.2 years to traverse the gap. The Voyager 1 spacecraft, traveling faster than any human-made object to date, would take tens of thousands of years to approach that distance. Concepts involving advanced propulsion remain theoretical, far from practical realization. The nearness that appears manageable on a galactic scale does not translate into immediate accessibility. Proxima Centauri b stands at the edge of familiarity and limitation. It occupies a position close enough to measure with increasing precision, yet distant enough to resist direct exploration. In that quiet span between possibility and reach, it represents both our nearest step outward and a reminder of the vast scales that still separate observation from arrival. Far from the crowded intimacy of red dwarf systems, there exists a world that circles a star remarkably similar to our own. Kepler 452b moves around a G-type star whose light and temperature echo the Sun, yet whose age exceeds it by more than 1 billion years. In that added span of time lies a subtle difference, a shift in brightness that gently alters the balance of warmth across its orbit. Kepler 452b is slightly larger than Earth, its radius about 60% greater. That increase suggests a stronger surface gravity, capable of holding a denser atmosphere if volatile gases were available during its formation. A thicker atmosphere can trap heat more efficiently, influencing cloud formation, weather patterns, and long-term climate stability. While its exact composition remains uncertain, measurements indicate it is likely rocky rather than gaseous, placing it within the broad category of terrestrial planets. The star it orbits shines a little brighter than the Sun does today, a natural consequence of stellar evolution. As stars age, hydrogen in their cores diminishes and energy output rises gradually. Kepler 452b lies within the habitable zone of this older star, receiving a level of radiation that may resemble the amount Earth could encounter far in the future. In this sense, it serves as a possible analog not for Earth's present, but for its distant climate trajectory. Increased stellar energy might intensify greenhouse effects, warming oceans, and altering atmospheric chemistry over geological timescales. Climate models suggest that even a modest rise in stellar brightness can shift the equilibrium between incoming and outgoing heat. If carbon dioxide accumulates and water vapor amplifies warming, surface conditions could move toward a humid greenhouse state. Oceans might persist, yet evaporation rates could increase, thickening cloud layers and transforming weather patterns. Whether Kepler 452b has entered such a phase remains unknown, since its atmosphere cannot yet be directly sampled. The subtle dimming events recorded by the Kepler Space Telescope reveal its size and orbit, but not the full character of its skies. Because it orbits a sun-like star rather than a volatile red dwarf, Kepler 452b likely experiences fewer intense flares and a steadier flow of radiation. This stability could favor long-term atmospheric retention and geological processes such as plate tectonics, which on Earth help regulate carbon through cycles of uplift and erosion. At the same time, its greater age raises the possibility that internal heat has diminished, altering magnetic shielding and volcanic activity. In this distant system, more than 1,400 light years away, the idea of habitability stretches forward in time. Kepler 4, 5, 2. B stands as a reflection not of a twin Earth, but of an Earth that has aged under a gradually brightening star. Its orbit traces a path through familiar light, yet that familiarity carries the weight of cosmic years, suggesting how delicate balances evolve as stars slowly change. At the center of a quiet gravitational arrangement, three stars circle one another in slow, patient arcs. This is the Gliese 667 system, a compact triple-star configuration where two larger stars orbit at a distance, while a smaller red dwarf holds planets close to its dim light. Around that red dwarf moves a world designated Gliese 667 cc, a planet more massive than Earth and often described as a super-Earth. Its classification comes from its weight rather than its character. Estimates suggest a mass several times that of our planet, enough to generate stronger surface gravity and to compress its interior into dense layers of rock and metal. Such gravity would influence everything above the crust, shaping mountain height, atmospheric thickness, and the behavior of water if it is present. With greater gravitational pull, gases are held more tightly, allowing for the possibility of a dense envelope surrounding the planet. Gliese 667 cc lies within the temperate region of its red dwarf star, receiving an amount of energy comparable to Earth's share of sunlight. Yet the quality of that light differs. Red dwarfs emit more infrared radiation and less visible light, altering the way energy is absorbed and reflected. A planet in such an orbit may warm differently at its surface, depending on atmospheric composition and cloud coverage. Because it circles close to its star, tidal forces could have slowed its rotation until one hemisphere constantly faces the light. If tidal locking has occurred, atmospheric circulation would determine whether warmth spreads evenly or collects on one side. The surrounding stellar architecture adds another dimension. While Gliese 667 cc orbits its red dwarf closely, two companion stars trace broader paths around the system's center of mass. Their distant presence alters the gravitational environment over long timescales, yet does not flood the planet with additional heat. The red dwarf remains the primary source of energy, small and steady, though capable of occasional flares that may influence atmospheric chemistry. Surface conditions remain uncertain. The planet's greater mass might imply higher pressure at ground level if a thick atmosphere exists. Elevated pressure could allow liquid water to persist at temperatures slightly beyond Earth's familiar range, extending the margin of potential stability. At the same time, a dense atmosphere might produce a pronounced greenhouse effect, lifting average temperatures above moderate levels. Without direct measurement of its spectral fingerprints, these possibilities remain theoretical. Gliese 667 cc illustrates how mass, stellar type, and orbital distance intertwine. It is larger than Earth, bathed in cooler starlight, and positioned within a narrow corridor of energy that suggests temperate conditions are plausible. Yet, stronger gravity and atmospheric uncertainties complicate the portrait. Within this layered triple star system, habitability is shaped by forces both intimate and distant, reminding us that even a familiar measure of energy can yield very different worlds when gravity and starlight combine in new ways. The phrase Earth-like is often spoken softly in planetary science, as though it carries both promise and caution. It does not describe a single trait, but a convergence of many. A world begins to resemble Earth when its size falls within a narrow window, roughly zero point 0.8 to 1.5 Earth radii. Below that range, gravity weakens and atmospheres may escape into space. Above it, gravity strengthens to the point where thick layers of gas can accumulate, blurring the boundary between rocky planet and miniature giant. Composition matters as much as scale. A rocky planet forms from heavier elements, building a solid surface of silicates and metals. Gas giants, even small ones, gather thick envelopes of hydrogen and helium that conceal any solid core beneath crushing pressure. An Earth-like world requires a crust where oceans can pool and continents can rise, rather than a deep atmosphere with no defined ground. Density measurements, drawn from gravitational influence and transit depth, help distinguish between these possibilities. Atmospheric retention shapes climate over immense spans of time. A planet must hold onto gases that moderate temperature and protect surface chemistry. Surface pressure determines whether liquid water can persist or whether it will evaporate into vapor or freeze into ice. On Earth, pressure and temperature intersect in a range that supports flowing water. Alter either variable significantly, and the balance shifts. Carbon dioxide, nitrogen, and water vapor interact in layered feedbacks that regulate heat, while trace gases influence radiation in subtle ways. Magnetic shielding adds another quiet requirement. Beneath Earth's crust, a molten outer core circulates, generating a magnetic field that deflects charged particles streaming from the sun. Without such protection, stellar winds can gradually erode atmospheric layers. Evidence from Mars suggests that the loss of its magnetic field coincided with significant atmospheric thinning. For distant exoplanets, magnetic properties are inferred indirectly, yet they remain essential in evaluating long-term stability. The nature of the host star also shapes Earth-likeness. A stable star with consistent energy output allows climates to settle into equilibrium. Highly variable stars, prone to frequent flares, can disrupt atmospheric chemistry and challenge retention. Even within calm systems, stellar brightness evolves slowly over billions of years, altering the habitable zone and reshaping planetary conditions. Axial tilt introduces another dimension. Earth's modest tilt creates seasons, distributing heat across latitudes and preventing extremes from remaining fixed. Too great a tilt could produce severe seasonal contrasts, while no tilt at all might lead to stagnant climatic patterns. Orbital eccentricity further influences temperature swings as elongated paths bring planets closer to and farther from their stars. Taken together, these factors reveal that Earth-likeness is not a simple checklist, but a dynamic interplay. Size, composition, atmosphere, magnetic field, stellar behavior, and orbital geometry all intertwine. A planet may share one or two familiar traits while lacking others, shifting it along a broad spectrum rather than into a precise category. In that spectrum, resemblance becomes a matter of degree, shaped by gravity and light, by rotation and time, forming worlds that echo Earth without fully repeating it. Every planet's fate begins not with its own mass or atmosphere, but with the star that anchors its orbit. Stars determine the rhythm of energy, the quality of light, and the span of time available for climates to settle and evolve. In studying distant worlds, it becomes clear that habitability is inseparable from stellar character. Sun-like stars, classified as G-type, burn steadily for billions of years. Their light is balanced across visible wavelengths, providing consistent energy that allows atmospheres to regulate temperature through long cycles. Our own sun is middle aged, stable, and comparatively calm. It brightens gradually over immense timescales, offering a wide and predictable habitable zone that migrates slowly outward as hydrogen in the core is consumed. Red dwarfs, by contrast, are smaller and cooler. They emit most of their energy in infrared light and possess far lower luminosity because they burn fuel slowly and efficiently. Their lifespans stretch into trillions of years, far exceeding that of sun-like stars. In theory, such longevity offers extended opportunities for planetary environments to stabilize and potentially sustain life. A world orbiting a red dwarf could experience an almost unchanging star for spans far longer than Earth has existed. Yet that abundance of time is accompanied by volatility. Young red dwarfs are often magnetically active, releasing intense flares and streams of charged particles. These bursts can dramatically increase radiation levels for planets in close orbit, altering atmospheric chemistry or gradually eroding protective layers. Since the habitable zone of a red dwarf lies close to the star, planets within it endure repeated exposure to this activity. Even as the star ages and activity declines, the early epochs may have shaped planetary conditions in decisive ways. Sun-like stars flare less frequently and with lower intensity relative to their output. Their greater brightness pushes habitable zones farther outward, reducing tidal locking and allowing planets to rotate more freely. However, they are less common within the galaxy. The majority of stars in the Milky Way are red dwarfs, small and numerous, forming the quiet background of stellar population. Their dominance means that statistically, many potentially temperate planets orbit these cool stars rather than stars like the Sun. This creates a trade-off between abundance and stability. Red dwarfs offer sheer numbers and extraordinary lifespans, but introduce higher radiation risks and close orbital configurations. Sun-like stars provide steadier illumination and broader orbital spacing, yet they are fewer and evolve more rapidly toward increased brightness. In weighing stellar types, the search for habitable worlds becomes a study of balance across cosmic time. A planet's potential is shaped by the energy that bathes it, by the frequency of stellar outbursts, and by the gradual evolution of the star itself. Light is not merely warmth, it is a governing influence that sculpts atmospheres, sets climatic boundaries, and defines the temporal window within which life, if it arises, might endure. Rotation is often taken for granted, a steady turning that brings dawn and dusk in gentle succession. Yet for many planets orbiting close to their stars, that rotation slows under the pull of gravity until movement and orbit become synchronized. This state, known as tidal locking, binds a planet so that one hemisphere continually faces its star while the opposite side remains turned away. The same face greets the light again and again as the far side lingers in shadow. Such alignment emerges gradually. Gravitational forces stretch a planet slightly along the line, connecting it to its star. Over long spans of time, this distortion dissipates rotational energy, easing the spin until the period of rotation matches the period of revolution. Our moon is tidally locked to Earth, always showing the same surface. On exoplanets that orbit near dim stars, the process unfolds more quickly because gravitational forces grow stronger with proximity. The immediate image suggests stark contrast. One hemisphere might endure perpetual daylight, absorbing continuous radiation, while the other lies in enduring darkness. Temperature differences could become extreme if no mechanism exists to redistribute heat. Early assumptions portrayed such worlds as divided between a scorched side and a frozen wasteland, each hostile in its own way. Yet modern climate models offer a more nuanced portrait. Simulations that incorporate atmospheric physics reveal how winds and pressure gradients might arise along the boundary between light and shadow. Heated air on the day side would expand and rise, flowing toward cooler regions before sinking and returning along the surface. This circulation can transport energy across the globe, softening temperature extremes. The effectiveness of such transport depends on atmospheric thickness and composition. A thin atmosphere might struggle to balance the gradient, while a denser one could spread warmth more evenly. Between the bright hemisphere and the dark lies a region often described as the terminator line, where starlight skims the horizon in constant twilight. In some models, this narrow band maintains moderate temperatures, neither intensely heated nor deeply frozen. If liquid water exists, it could persist within this zone, forming oceans or cloud systems that stabilize conditions further. The existence and breadth of such a region depend on the interplay between radiation, rotation, and atmospheric dynamics. Tidal locking therefore reshapes climate, but does not automatically preclude stability. Oceans, if present, can also carry heat, circulating through currents that respond to wind patterns. Cloud cover on the day side may reflect incoming radiation, moderating surface temperatures. Even the night side, though colder, might retain sufficient atmospheric insulation to prevent complete collapse of gases. In this synchronized dance between planet and star, extremes yield to complexity. The absence of a familiar day-night cycle introduces new patterns rather than simple ruin. Habitability under tidal locking becomes a question of circulation and resilience, guided by physics that allows balance to emerge even in a world that no longer turns freely toward the light. Light carries more than brightness. It carries memory. When a planet passes in front of its star, a small portion of starlight filters through the thin shell of gases surrounding that distant world. In that brief passage, atoms and molecules imprint subtle patterns upon the beam, absorbing specific wavelengths while allowing others to continue onward. This delicate filtering forms the foundation of spectroscopy, the practice of separating light into its constituent colors to read the chemical traces hidden within. Each molecule interacts with light in a characteristic way. Water vapor absorbs energy at distinct infrared wavelengths. Carbon dioxide leaves its own recognizable gaps, and methane etches narrower features across the spectrum. By comparing observed spectra to laboratory measurements made on Earth, astronomers infer the presence of these gases without ever sampling them directly. The result is not an image of clouds or skies, but a set of spectral fingerprints, faint yet interpretable. The James Webb Space Telescope operates primarily in the infrared, an ideal range for detecting atmospheric molecules that absorb heat positioned beyond Earth's atmosphere. It avoids much of the interference that blurs ground-based measurements. When an exoplanet transits its star, Webb records the minute differences in stellar light before, during, and after the event. From those variations, scientists extract transmission spectra that reveal how gases shape the passing light. In some cases, additional observations measure thermal emission as a planet moves behind its star, offering hints about atmospheric temperature and composition. Water vapor has already been detected in several exoplanet atmospheres, particularly on large hot worlds where signals are stronger. Carbon dioxide signatures have also appeared, their absorption features rising above instrumental noise. Methane remains more elusive, as its signals can overlap with other compounds and are easily masked by clouds or hazes. The interpretation of these spectra requires careful modeling, accounting for temperature, pressure, and chemical interactions that influence how molecules behave. Detection is challenging because the signals are extraordinarily small. A planet's atmosphere may alter starlight by a fraction of a percent, a difference that must be distinguished from stellar activity and instrumental variation. Stars themselves are dynamic, with spots and flares that can introduce fluctuations resembling atmospheric features. Data reduction techniques attempt to isolate planetary signals from these background changes, but uncertainty remains inherent. False positives complicate the picture further. Oxygen or methane alone do not guarantee biological activity, since non biological processes can produce similar signatures under certain conditions. Ultraviolet radiation can break apart water molecules, leaving oxygen behind without life's involvement. Geological reactions can generate methane independent of living organisms. For this reason, scientists seek combinations of gases and contextual clues rather than single indicators. In studying atmospheres we cannot see, the search relies on patience and precision. Each spectrum is a layered message encoded in light, shaped by molecules drifting above an unseen surface. From these faint patterns, a portrait slowly forms, incomplete yet revealing, drawn not with images, but with the quiet language of absorption and wavelength. Not every temperate planet must resemble Earth's familiar balance of land and sea. Some models suggest a different possibility, a world where water dominates entirely, forming a global ocean that stretches unbroken from horizon to horizon. On such planets, continents never rise above the surface, and coastlines never interrupt the meeting of sky and sea. The entire exterior becomes a single, continuous expanse of liquid. These ocean worlds are thought to form beyond the frost line of their systems, where ice and volatile compounds are abundant during planetary assembly. If such a planet later migrates inward to a warmer orbit, its accumulated ices could melt, producing oceans far deeper than any on Earth. Estimates suggest depths reaching tens or even hundreds of kilometers. Beneath that vast column of water, pressure increases steadily, compressing the liquid into forms unfamiliar at Earth's surface. At sufficient depth, water transitions into high-pressure ice, crystalline structures that remain solid despite elevated temperatures. Unlike the floating ice that forms in Earth's polar regions, these phases sink, creating a dense layer between the ocean above and the rocky mantle below. This separation may isolate the water from the planet's crust, limiting direct chemical exchange. On Earth, the interaction between seawater and minerals at hydrothermal vents plays a crucial role in cycling nutrients and sustaining ecosystems. On an ocean world sealed by high-pressure ice, such exchanges could be diminished or altered. The absence of continents carries climatic implications as well. Land masses on Earth influence atmospheric circulation, shape ocean currents, and contribute to long-term carbon cycling through weathering. Without exposed rock, processes that regulate carbon dioxide over geological timescales might operate differently. A planet covered entirely by ocean could experience a more uniform climate with fewer regional contrasts. Yet it may also lack mechanisms that stabilize temperature through feedback between land and atmosphere. Despite these differences, deep oceans offer intriguing potential for life. Liquid water remains a powerful solvent, and sunlight penetrating upper layers could sustain photosynthetic chemistry if atmospheric conditions permit. In deeper zones, geothermal heat might generate circulation patterns within the ocean itself, even if direct contact with rock is limited. Internal heating from radioactive decay or tidal forces could maintain warmth beneath the surface, preventing complete freezing in colder environments. Ocean worlds expand the concept of habitability beyond familiar geography. They suggest that a planet need not mirror Earth's continents and shallow seas to host complex chemistry. Instead, habitability becomes a question of pressure, depth, and circulation within a global ocean. In these vast aqueous environments, the boundary between sea and sky defines the entire planetary surface, shaping climates and possibilities in ways that differ from terrestrial experience, yet remain grounded in the same fundamental properties of water and energy. Between the scale of our planet and the smaller gas giants lies a category that has no direct counterpart in our solar system. These are the super-Earths, worlds larger than Earth yet smaller than Neptune, occupying a range of sizes and masses that blur familiar boundaries. Some measure only slightly wider than our planet, while others approach twice its radius. Their gravity strengthens accordingly, shaping both interior and atmosphere in ways that remain under study. With greater mass comes a deeper gravitational well. Super-Earths are more capable of holding on to light gases, preventing atmospheric escape over long spans of time. This retention may result in thicker atmospheric envelopes, potentially rich in carbon dioxide, nitrogen, or even hydrogen, depending on formation history. A dense atmosphere can intensify greenhouse effects, trapping heat and influencing surface temperature. It may also increase surface pressure, altering the behavior of water and the chemistry of rock. Yet, classification does not guarantee composition. Some super-Earths are dense and rocky, resembling scaled-up terrestrial planets. Others may possess significant layers of volatiles, transitioning toward what are sometimes called mini-Neptunes. Distinguishing between these possibilities depends on measuring both radius and mass to determine bulk density. Even then, interior structure remains uncertain. A planet slightly larger than Earth might contain a proportionally larger iron core, or instead, a thick mantle rich in silicates. These internal differences influence magnetic field generation and volcanic activity, which in turn shape atmospheric evolution. Geology on a super-Earth could differ substantially from Earth's familiar patterns. Higher gravity compresses crust and mantle materials, potentially affecting how heat moves through the interior. Plate tectonics on Earth relies on convection within the mantle and the balance between crustal thickness and gravitational forces. On a super-Earth, stronger gravity might either enhance or inhibit tectonic cycling. Some models suggest increased internal heat from radioactive decay and residual formation energy could drive vigorous mantle convection. Others indicate that thicker lithospheres might resist subduction, limiting the recycling of carbon between surface and interior. The presence or absence of plate tectonics carries implications for climate regulation. On Earth, tectonic activity supports a carbon cycle that moderates atmospheric composition over millions of years. If a super-Earth lacks such recycling, its atmosphere may evolve along a different path, either accumulating greenhouse gases or losing them without replenishment. Surface conditions would respond accordingly, shaping oceans, continents, or perhaps global atmospheres without stable land masses. Super-Earths expand the spectrum of possible habitable environments, yet they also complicate it. Their stronger gravity, thicker atmospheres, and uncertain internal dynamics introduce variables absent from our planetary reference. They are not simply enlarged versions of Earth, but distinct worlds governed by intensified forces. Within that increased scale, familiar processes may operate in unfamiliar proportions, creating climates and landscapes that echo terrestrial principles while diverging in fundamental ways. Long before thousands of distant planets were catalogued, astronomers attempted to frame the search for intelligence within a single line of reasoning. The result was the Drake equation, a structured way of estimating how many communicative civilizations might exist within the Milky Way. It does not predict, it organizes uncertainty. Each term represents a step along a long chain, beginning with the rate at which stars form and narrowing toward the fraction of worlds where technology might arise. The first factors concern astronomy. How many stars are born each year, and how many possess planetary systems? For decades, even the presence of planets beyond our own system remained unconfirmed, leaving those early terms largely speculative. Subsequent variables address the fraction of planets that could support life, the fraction on which life actually emerges, and the proportion that develop intelligent, technologically capable societies. Each stage reduces the number, not through dismissal, but through layers of probability. What became clear over the past 3 decades is that the earlier astronomical terms were far less restrictive than once imagined. The discovery of thousands of exoplanets revealed that planetary systems are common rather than rare. Many stars host multiple worlds, and small rocky planets appear frequently across the galaxy. This shift recalibrated the first portion of the equation. Instead of guessing whether planets existed elsewhere, astronomers now treat them as abundant features of stellar evolution. Yet abundance of planets does not equate to abundance of life. The equation moves from measurable astrophysics into biology and sociology, domains where data remain limited to a single example. On Earth, life arose relatively early in planetary history, suggesting that under suitable conditions, it may not require extraordinary time. However, the transition from microbial life to complex, technological societies involves additional thresholds whose probabilities are unknown. Each unknown multiplies across the equation, widening the range of possible outcomes from near solitude to a galaxy populated with civilizations separated by vast distances. Habitability occupies only one segment within this framework. A planet may lie within a temperate orbit and possess water, atmosphere, and geological stability, yet still remain lifeless. Chemical pathways that lead from simple molecules to self-replicating systems may depend on circumstances not fully understood. Even if life becomes established, evolutionary pressures and planetary histories shape whether intelligence arises at all. The Drake equation, therefore, serves less as a calculation and more as a reflection of layered uncertainty. It connects the measurable prevalence of stars and planets to the far less certain development of communication and culture. In the context of exoplanet discovery, its early terms have grown more concrete, informed by observation rather than speculation. The later terms, however, remain open, grounded in a single biosphere, known intimately yet insufficient to define the cosmos. A planet's atmosphere can carry hints not only of chemistry but of activity. Among the many gases that may drift through alien skies, certain combinations draw careful attention because, on Earth, they are closely tied to life. These potential indicators are known as biosignatures, patterns within atmospheric composition that suggest ongoing biological processes rather than simple geological reactions. Oxygen stands as one of the most prominent examples. On Earth, vast quantities of oxygen exist because photosynthetic organisms continuously replenish it. Without that steady input, oxygen would gradually react with surface minerals and decline over time. Detecting substantial oxygen in a distant atmosphere therefore raises interest, especially if it appears alongside gases that would normally react with it, yet oxygen alone does not confirm biology. Under certain stellar conditions, ultraviolet radiation can split water vapor high in the atmosphere, allowing hydrogen to escape while oxygen remains behind. In such cases, an oxygen-rich atmosphere might emerge without any living organisms. Methane provides another piece of the puzzle. On our planet, methane is produced both biologically and geologically, but its persistence in the presence of oxygen requires constant renewal. If methane and oxygen coexist in significant amounts within an exoplanet atmosphere, it suggests a dynamic imbalance that may point toward biological replenishment. The key lies in the relationship between gases rather than in the presence of one alone. Chemical disequilibrium, where compounds that should quickly react remain abundant together, can signal ongoing processes that prevent equilibrium from settling. Seasonal changes add an additional layer of subtlety. On Earth, atmospheric carbon dioxide fluctuates with plant growth cycles, rising and falling as vegetation absorbs and releases it. Detecting similar periodic variations in an exoplanet's atmosphere could hint at surface level processes linked to climate and perhaps life. Such measurements require extraordinary precision, tracking spectral features over multiple orbits to distinguish genuine cycles from observational noise. False positives remain a persistent concern. Geological activity can release methane through volcanic processes, and photochemical reactions in unusual atmospheres can produce gases that mimic biological signatures. Even oxygen and ozone can accumulate abiotically under specific conditions involving stellar radiation and planetary history. Interpreting these signals demands caution. Integrating knowledge of the host star, planetary mass, temperature, and overall atmospheric composition. For this reason, researchers seek multiple lines of evidence before drawing conclusions. A compelling biosignature would likely involve a combination of gases maintained in chemical imbalance, supported by contextual clues about surface temperature and stellar influence. Spectroscopy provides the data, but interpretation relies on modeling and comparison to planetary environments, both within and beyond our solar system. In the search for life, biosignatures represent patterns rather than declarations. They are subtle arrangements of molecules within drifting air, shaped by physics, chemistry, and potentially biology. Reading them requires patience, acknowledging that life's imprint, if present, may be woven into atmospheric chemistry in ways that demand careful and layered interpretation. In the middle of the 20th century, during a casual lunchtime conversation, physicist Enrico Fermi posed a remark that would echo far beyond the table where it was spoken. Surrounded by colleagues and aware of the immense scale of the Milky Way, he considered the growing understanding of stars and planetary systems, and then distilled his thoughts into a simple challenge. If the galaxy is so vast and so old, and if life could arise elsewhere, the sky should carry some sign of it. His question became known as the Fermi paradox. The paradox rests on contrast. The Milky Way contains hundreds of billions of stars, many older than the Sun. Even if only a small fraction host temperate planets, the timescales involved are staggering. Civilizations, with technologies only slightly more advanced than our own could, in principle, spread across the galaxy in periods far shorter than its age. Signals, probes, or detectable alterations of starlight might accumulate over millions of years. Yet when astronomers listen for artificial transmissions or examine the heavens for unmistakable engineering, they encounter quiet. That silence does not necessarily imply absence. It highlights the distance between habitability and civilization. A planet may possess water, atmosphere, and stable climate, yet never develop complex organisms. Evolution on Earth required billions of years to move from microbial life to multicellular forms, and only a small portion of that history includes technological intelligence. The path from chemistry to consciousness appears neither automatic nor guaranteed. Other explanations extend beyond biology. Civilizations may arise but remain short lived, limited by self imposed or environmental constraints. They may choose not to transmit signals or use methods beyond our current capacity to detect. Interstellar distances dilute communication, and the window during which two societies overlap in time may be narrow. Even a galaxy populated with life could appear silent if technological phases seldom coincide. The growing catalog of potentially habitable worlds deepens rather than resolves the paradox. Each new discovery increases the number of environments where life might take hold, yet none yet display evidence of technology. Observations refine the early terms of equations estimating abundance, while the later terms remain speculative. The quiet sky becomes more striking as the count of planets grows. Fermi's observation does not diminish the search, it frames it. The existence of temperate worlds establishes that suitable conditions may be widespread, but it does not bridge the gap between environment and expression. Civilization requires not only a hospitable planet, but time, stability, and a sequence of developments that remain only partially understood. In the vast expanse between stars, silence may reflect rarity, distance, timing, or simply the limits of our instruments. The paradox endures as a reminder that habitable does not mean inhabited, and that life, particularly intelligent life, may occupy a far narrower niche than planetary abundance alone would suggest. Distance in space is measured not in kilometers, but in time. A light year is the span light travels in 1 year, moving at roughly 300,000 kilometers per second. In that time, a beam crosses nearly 9.46 trillion kilometers. When a planet is said to lie 4 light years away, it means the light leaving its star today will arrive here 4 years later. The measure feels abstract until one considers the limits of physical travel. The fastest human-made object, Voyager 1, drifts outward from the solar system at about 17 kilometers per second. That speed once carried it past the giant planets in mere years, yet against interstellar scale it becomes modest. At its current velocity, Voyager 1 would require more than 70,000 years to approach a star 4 light-years distant. The spacecraft was not designed for such a journey. Its trajectory is a gentle outward arc, propelled only by the momentum granted at launch and planetary assists. The gulf between light speed and achievable propulsion defines the challenge. Chemical rockets rely on combustion and expel propellant to generate thrust. To approach even a fraction of light speed using conventional fuel would demand energy and mass far beyond current capacity. The equations governing motion require that increasing velocity multiplies fuel needs in exponential fashion. Concepts involving nuclear fusion, antimatter, or light sails remain theoretical or experimental, constrained by engineering limits and resource availability. Generational travel has been proposed as an alternative, envisioning spacecraft large enough to sustain human communities for centuries. Such vessels would carry life support systems, food production, and closed ecological cycles. Even at relatively high speeds, the voyage to nearby stars would span multiple human lifetimes. Societies would depart knowing that arrival would be experienced only by descendants. The social and biological challenges of maintaining stability over centuries are as formidable as the technical ones. Energy requirements compound the difficulty. Accelerating a spacecraft with substantial mass to even a tenth of light speed demands an energy output comparable to the total consumption of entire nations over extended periods. Deceleration upon arrival doubles the requirement, since the craft must shed the kinetic energy it once gained. Shielding against interstellar particles becomes critical as velocity increases. Even tiny grains of dust would strike with tremendous force at high speeds. For now, our exploration remains rooted in observation rather than visitation. Telescopes collect photons that have crossed light years effortlessly, carrying spectral information without expenditure of fuel. The planets revealed by these signals reside within distances measurable in years for light, yet in tens of thousands for machines built today. The separation underscores how near and far coexist in the same phrase. Nearby, in astronomical terms, still lies far beyond the reach of current propulsion, leaving these worlds as destinations of thought rather than travel. Even the largest telescopes do not truly see exoplanets in the way the eye sees a neighboring world. At interstellar distances, planets lie so close to their stars in angular separation that they blur into a single point of light. Resolution, the ability to distinguish two objects as separate, is limited by both aperture size and wavelength. A planet the size of Earth orbiting a sun-like star many light years away would appear billions of times fainter than the star itself, and separated by an angle smaller than a fraction of a pixel in most instruments. Direct imaging therefore faces two intertwined difficulties: separation and contrast. The star's glare overwhelms the faint reflected light from its planet, much like trying to discern a firefly beside a searchlight from thousands of kilometers away. Even with space-based observatories positioned beyond atmospheric distortion, diffraction spreads starlight outward, creating a halo that obscures dim companions. To counter this, astronomers use coronagraphs, instruments that block the central starlight to reveal nearby objects. Yet the suppression must be extraordinarily precise, reducing stellar brightness by factors of billions while preserving the planet's faint glow. Current telescopes can directly image some large exoplanets, particularly young gas giants, orbiting far from their stars. These planets emit residual heat from formation and sit at wider orbital distances, making them easier to isolate from stellar glare. Earth-sized planets in temperate orbits remain beyond consistent direct detection. Instead, most knowledge continues to rely on indirect methods, inferring properties from light curves and spectra rather than photographs. Future mission concepts aim to narrow that gap. The LUVOIR concept, a proposed large ultraviolet optical infrared observatory, envisions a space telescope with a mirror far larger than any currently in operation. Paired with advanced coronagraphs or a free-flying starshade that blocks starlight before it enters the telescope, such a mission could resolve Earth-sized planets around nearby stars. With higher resolution and improved contrast, it might analyze atmospheric composition directly, searching for biosignatures with greater confidence. Yet technological bottlenecks remain formidable. Building and launching mirrors of enormous diameter require engineering solutions that balance weight, rigidity, and deployment in space. Precision alignment must be maintained over vast distances and temperature fluctuations. Instruments must minimize internal noise and vibration, achieving stability measured in nanometers. Funding and collaboration across agencies add practical constraints beyond physics alone. For now, the search advances within these boundaries. Each improvement in optics and detector sensitivity expands the horizon incrementally. The planets themselves do not change, but our capacity to resolve their faint light evolves slowly. Between possibility and proof stands the current limit of technology, not as a barrier in principle, but as a threshold that awaits refinement through design, patience, and careful construction. Far beyond Earth's atmosphere, positioned nearly 1.5 million kilometers from our planet, a segmented mirror unfolds in the cold of space. The James Webb Space Telescope orbits the Sun at a gravitational balance point, shielded from heat by a multi-layer sunshade the size of a tennis court. In that shadowed stillness, its instruments observe the universe, primarily in infrared light, a wavelength range well suited to detecting heat signatures and molecular absorption. Infrared capability distinguishes Webb from previous observatories. Many key atmospheric gases absorb and emit strongly in this portion of the spectrum, including water vapor, carbon dioxide, and methane. When an exoplanet passes before its star, a portion of starlight travels through the planet's atmosphere before reaching the telescope. Webb separates that light into its spectral components with exceptional sensitivity, searching for subtle dips that correspond to specific molecules. The process demands stability measured in fractions of a percent, as atmospheric signatures often alter the incoming light only slightly. In its early years of operation, Webb has already detected carbon dioxide in the atmospheres of hot gas giants, confirming its ability to identify complex molecules beyond the solar system. It has observed water vapor on several exoplanets and begun refining estimates of temperature and cloud structure. In some cases, data indicate thick hazes that obscure deeper atmospheric layers, revealing that interpretation depends not only on detection but on understanding how light interacts with clouds and aerosols. These findings demonstrate that atmospheric chemistry on distant worlds can be measured rather than merely hypothesized. Webb's strength lies not only in sensitivity but in precision over repeated observations. By monitoring multiple transits of the same planet, it reduces uncertainty and refines spectral features. It can also analyze secondary eclipses when a planet moves behind its star, isolating the planet's own thermal emission. From these observations, researchers infer atmospheric temperature profiles and possible circulation patterns, assembling a layered portrait of climates far beyond direct reach. Yet Webb is not designed to resolve Earth-sized planets around Sun, like stars, in reflected light. Its mirror, though large by current standards, does not provide the contrast required for consistent direct imaging of true Earth analogs. Instead, it serves as a bridge between indirect detection and future observatories with even greater capabilities. Each spectrum collected expands the library of atmospheric behavior under diverse conditions, informing models that will guide the next generation of instruments. In this role, Webb represents a threshold rather than an endpoint. It translates faint infrared signals into chemical narratives, revealing that exoplanet atmospheres can be studied with increasing clarity. The telescope's discoveries mark the beginning of a more detailed era, where distant worlds are no longer defined solely by mass and orbit, but by the composition and structure of the air that surrounds them. Among the thousands of exoplanets catalogued so far, patterns begin to emerge. Most confirmed worlds do not mirror Earth in size or setting. Many are larger, falling into the category of super-Earths or mini-Neptunes, bodies whose greater mass allows them to retain thicker atmospheres. These envelopes often alter surface conditions in ways that diverge from terrestrial experience, raising pressures and intensifying greenhouse effects. A planet slightly larger than Earth may remain rocky, yet its scale alone introduces differences that ripple through climate and geology. Stellar context also shapes the distribution. A significant portion of detected temperate planets orbit red dwarfs, not sun-like stars. This reflects both the abundance of red dwarfs in the galaxy and the relative ease of detecting planets in close orbits around smaller, dimmer stars. Because red dwarfs are faint, the relative dip in brightness caused by a transiting planet appears more pronounced. Their habitable zones lie nearer to the star, increasing the likelihood of repeated, observable transits within a short span of time. As a result, surveys reveal a landscape dominated by close orbiting planets around these cool stars. Sun-like systems are less common in stellar population and more challenging to examine for Earth-sized companions. The greater brightness and larger radii of G-type stars reduce the relative signal of small transiting planets. Detecting a world the size of Earth at a distance similar to Earth's orbit requires long observation periods and extraordinary precision. Even when such candidates are identified, confirming their masses and densities demands careful follow-up with radial velocity measurements that approach instrumental limits. True Earth analogs demand more than size and orbit. They must combine terrestrial radius, rocky composition, temperate insolation, stable atmospheric retention, and a star with manageable variability. Each additional criterion narrows the field. A planet may satisfy two or three of these conditions, yet diverge on another, shifting it along a spectrum of resemblance rather than into precise equivalence. Statistical analyses of data from missions, such as Kepler, suggest that small rocky planets in temperate zones may not be rare in an absolute sense. However, when constrained to Sun-like stars and Earth-sized radii within similar orbital distances, the numbers thin. The perfect twin, matching Earth in both physical scale and stellar environment, remains unconfirmed. Candidates exist that approach these criteria, but uncertainties in composition, atmospheric properties, and stellar evolution persist. In the expanding catalog of distant worlds, Earth appears neither singular nor easily replicated. Planets of many kinds fill the galaxy, yet the specific combination of traits that defines a close analog continues to elude precise identification. The search has revealed diversity and abundance, while the exact echo of our own world remains, for now, undiscovered within the limits of present observation. A planet may rest within a temperate orbit and still drift beyond the boundary of life's comfort. The line between habitable and hostile is narrow, shaped by processes that can amplify small imbalances into lasting extremes. One such process is the runaway greenhouse effect, a feedback cycle in which warming intensifies itself. As surface temperatures rise, more water evaporates into the atmosphere. Water vapor traps additional heat, raising temperatures further and driving yet more evaporation. Over time, oceans can diminish, and the atmosphere thickens with heat-retaining gases, transforming a once moderate climate into a furnace. The transformation of Venus offers a reminder that proximity alone does not determine fate. Even without runaway warming, stellar radiation can erode a planet's atmosphere gradually, Energetic particles emitted during flares and sustained stellar winds collide with upper atmospheric layers, imparting energy that allows lighter molecules to escape into space. Over millions or billions of years, this loss thins protective gases, reducing surface pressure and exposing the ground to increased ultraviolet radiation. Planets orbiting active red dwarfs are particularly vulnerable, especially during early stellar phases when magnetic activity runs high. Magnetic fields provide a countermeasure, deflecting charged particles and preserving atmospheric integrity. Generated by convection within a molten core, a magnetic shield depends on internal heat and planetary rotation. Should that internal dynamism wane, the field may weaken or vanish. Without it, stellar particles interact directly with atmospheric constituents, accelerating escape and altering chemistry. A world's internal structure, therefore, influences surface conditions through invisible forces extending far beyond its crust. Atmospheric collapse presents another pathway to uninhabitability. On planets with limited greenhouse gases or reduced stellar input, temperatures may fall below the threshold required to maintain gases in the vapor phase. Carbon dioxide and even nitrogen can condense or freeze onto the surface, thinning the atmosphere and reducing pressure further. As the air diminishes, liquid water becomes unstable, and the climate shifts toward a frozen equilibrium. Mars illustrates aspects of this process, where atmospheric thinning contributed to surface conditions that no longer support persistent liquid water. Extreme volcanism can also reshape habitability. While moderate volcanic activity replenishes atmospheric gases and supports chemical cycles, excessive outgassing can saturate the atmosphere with carbon dioxide or sulfur compounds. Persistent eruptions release aerosols that alter cloud formation and surface temperatures. In the absence of regulatory feedback, such activity may drive oscillations between intense warming and prolonged cooling. These mechanisms demonstrate that habitability depends on balance maintained over long timescales. Radiation, internal heat, atmospheric chemistry, and orbital position interact continuously. A planet may begin with favorable conditions, yet subtle shifts accumulate, redirecting climate toward states incompatible with liquid water. In this quiet interplay of energy and matter, the margin for stability remains delicate, sustained only when multiple systems operate in concert rather than in excess. Not every comparison with Earth tilts toward deficiency. In the wide range of planetary possibilities, some worlds may possess conditions that extend stability beyond what our own planet experiences. The idea of a planet better suited for long-term equilibrium does not require perfection, only variations that favor endurance across immense spans of time. A star, slightly smaller than the Sun, offers one such variation. These orange K-type stars shine less intensely and consume their fuel more slowly, granting lifespans that stretch far beyond the Sun's projected 10 billion years. Their energy output changes gradually, allowing habitable zones to remain relatively steady for tens of billions of years. A planet orbiting within such a zone would experience a longer window during which surface temperatures remain moderate. Extended stellar stability provides more time for biological complexity to arise and adapt without the pressure of rapid brightening. Planetary mass also shapes potential advantage. A world with slightly stronger gravity than Earth's could retain its atmosphere more effectively, reducing the gradual escape of lighter molecules. Thicker air, if not excessive, can help moderate temperature by distributing heat and sustaining liquid water across varied latitudes. Stronger gravity may also maintain internal heat longer, preserving a molten core capable of generating a magnetic field. This internal dynamism supports shielding against stellar particles and sustains geological cycling over extended periods. Climate stability depends not only on stellar output, but on feedback systems within the planet itself. If tectonic processes regulate carbon dioxide efficiently, surface temperatures may fluctuate within narrower bounds. A balance between volcanic outgassing and chemical weathering can dampen extremes, preventing runaway greenhouse conditions or prolonged glaciation. Slight differences in ocean distribution and axial tilt might produce gentler seasonal contrasts, reducing environmental volatility while still promoting ecological diversity. Orbital architecture influences the frequency of catastrophic disruptions. In our solar system, Jupiter's gravity deflects many potential impactors, yet Earth has endured periodic asteroid and comet collisions that reshaped its biosphere. A planetary system with fewer residual planetesimals, or a configuration that sweeps debris outward early in its history, could experience fewer large impacts over time. Reduced collision rates would allow surface environments to remain undisturbed for longer intervals, enabling sustained biological evolution without repeated mass extinctions. None of these factors guarantee flourishing ecosystems, yet together they illustrate how variation can lean toward prolonged balance. A planet orbiting a long-lived, moderately luminous star, possessing slightly enhanced gravity, sustained tectonic cycling, and a relatively calm impact history, might maintain habitable conditions for periods exceeding Earth's current trajectory. In contemplating such possibilities, the concept of habitability expands from mere survival to resilience. Earth represents one successful example among many potential configurations. Somewhere beyond our view, conditions may converge in ways that extend stability further still, shaping climates that remain temperate under a quieter star, supported by gravity and geology that favor endurance across the unfolding ages. Time shapes planets long before life ever has a chance to take hold. A star forms within a collapsing cloud of gas and dust, and around it, a disk begins to spin. Within a few million years, grains of dust collide and clump, forming larger bodies that merge into planetesimals. Over tens of millions of years, repeated collisions build full-sized planets, their surfaces molten from the energy of impacts and radioactive decay. In cosmic terms, this assembly is swift, yet it leaves young worlds unstable and inhospitable. As cooling begins, atmospheres accumulate through volcanic outgassing and the delivery of volatile compounds by icy bodies. Oceans, if conditions allow, may condense within tens to hundreds of millions of years. On Earth, evidence suggests that liquid water appeared relatively early, but the transition from chemistry to biology required additional spans of time. Simple microbial life emerged within the first billion years, yet the development of complex multicellular organisms unfolded only after billions more had passed. Evolution proceeds not in steady increments, but through extended phases shaped by environmental shifts and chance events. Stars, too, follow long arcs of change. A star like the Sun brightens gradually over billions of years as hydrogen in its core is fused into helium. This slow increase in luminosity pushes the habitable zone outward. A planet that begins within a temperate orbit may eventually receive too much radiation, while a more distant world may enter a favorable range as the star ages. For smaller stars with extended lifespans, these habitable windows can remain open far longer, offering prolonged periods of stability. For more massive stars, rapid fuel consumption shortens the interval during which moderate temperatures persist. Habitability, therefore, is not fixed. It opens and closes over geological epochs. A planet may pass through multiple phases, from molten beginnings to temperate oceans to eventual extremes of heat or cold. Internal processes, such as tectonics and magnetic field generation, also evolve, influencing atmospheric retention and climate regulation. As radioactive elements decay and cores cool, magnetic shielding may weaken, altering how stellar radiation interacts with the atmosphere. The interplay of planetary development and stellar aging creates shifting corridors of opportunity. Life requires not only suitable conditions, but sufficient duration for complexity to emerge. Short-lived stars may offer warmth, but not the time needed for evolutionary pathways to unfold. Extremely long-lived stars provide extended illumination, yet early volatility might strip atmospheres before stability is reached. Across billions of years, planets and stars move through cycles that redefine their environments. Oceans appear and recede, atmospheres thicken or thin, and habitable zones migrate outward. Within these vast spans, the emergence of life depends on timing as much as temperature. Stability must persist long enough for biological processes to take root, adapt, and diversify, all within windows that gradually shift as stars age and planetary interiors cool. After decades of observation, a quieter form of discovery begins to take shape, not from a single planet, but from patterns emerging across thousands. The Kepler Space Telescope did not simply identify individual worlds. It surveyed a fixed patch of sky and counted how often stars dimmed in ways consistent with orbiting planets. From those counts, astronomers derived occurrence rates, translating detections into estimates of how common certain types of planets might be across the galaxy. Kepler's field contained over 100,000 stars, monitored continuously for years. Among them, small rocky planets appeared frequently, especially in short-period orbits. By correcting for the geometric bias that only a fraction of planets transit from our perspective, researchers extrapolated beyond the observed sample. The results suggested that planets are not rare outcomes of star formation, but common byproducts. Many stars host multiple worlds, and a significant fraction appear to possess planets roughly Earth-sized. When attention turns specifically to temperate orbits around Sun-like stars, the numbers narrow but remain notable. Statistical analyses estimate that between several percent and perhaps more than 20% of such stars may host an Earth-sized planet within their habitable zones. The range depends on assumptions about planetary size, thresholds, orbital distances, and detection completeness. Even the lower end implies that billions of potentially temperate planets could exist within the Milky Way. However, these estimates carry uncertainty margins. Kepler's sensitivity declined for planets with longer orbital periods, meaning that Earth analogs with year-long orbits were more difficult to confirm. Stellar noise, instrumental limits, and false positives introduce additional variability into occurrence rates. Some candidate planets remain unconfirmed, while others have been reclassified as data improved. As a result, reported percentages often include error bars reflecting statistical spread rather than precise counts. Different stellar types further complicate the picture. Red dwarfs, which dominate the galaxy numerically, appear particularly likely to host small rocky planets in temperate orbits. For Sun-like stars, the fraction is lower but still substantial. Extrapolation across the entire stellar population, therefore, yields a broad range of possibilities rather than a single definitive value. The emerging view suggests that habitable worlds, defined by size and insulation alone, may not be exceptional. Yet habitability in practice depends on atmospheric composition, magnetic shielding, and long-term stability, factors not captured in occurrence rates derived from transit surveys. Statistics provide a framework for abundance, while uncertainty reminds us that definitions remain layered and evolving. Within these margins of error, a remarkable shift has occurred. The question is no longer whether temperate Earth-sized planets exist beyond our solar system, but how frequently they appear. Precision will improve as new missions refine detection methods and extend observations, narrowing the bands of uncertainty that still surround these estimates. Our search has been shaped by familiarity. Telescopes scan for worlds that resemble our own because life here is the only example we understand in detail. We look for liquid water, temperate orbits, and atmospheres containing gases that biology on Earth would produce. This approach is practical, grounded in chemistry we have observed, yet it carries an inherent carbon bias. All known organisms rely on carbon's versatility, its ability to form stable, complex molecules. From that single data point, we infer that carbon-based life is the most likely elsewhere. Carbon's abundance in the universe strengthens this assumption. It forms easily within stars and binds readily with hydrogen, oxygen, and nitrogen. Water, too, is common, making the combination seem universal. Still, familiarity can narrow imagination. Silicon, though less flexible than carbon, shares some chemical properties. In environments vastly different from Earth's, alternative solvents such as liquid methane or ammonia might support unfamiliar biochemistries. While no direct evidence suggests such systems exist, chemistry does not forbid them under certain pressures and temperatures. Our instruments favor atmospheric detection, yet life may thrive beyond the reach of atmospheric signatures. Icy moons within our solar system hint at this possibility, hiding oceans beneath frozen crusts. On exoplanets, thick ice shells could conceal deep global seas warmed by internal heat rather than starlight. In such cases, surface conditions might appear hostile while subsurface environments remain stable and chemically active. Transit spectroscopy would reveal little of these hidden habitats, as their biological processes would not easily imprint on the thin upper atmosphere if one exists at all. Atmospheric composition itself may vary far from Earth's template. A biosphere could persist under a sky dominated by gases unfamiliar to human lungs. Oxygen, often proposed as a strong biosignature, did not dominate Earth's atmosphere for much of its history. Methane, carbon dioxide, or other compounds might reflect biological cycles that differ from those shaping our own planet. Interpreting such signals requires caution, since non-biological processes can also produce similar chemical imbalances. Even the concept of a habitable zone centers on surface liquid water, assuming a planet warmed primarily by its star. Worlds with thick hydrogen atmospheres could retain heat at greater orbital distances, expanding potential habitats beyond traditional boundaries. Conversely, tidally heated planets may sustain internal warmth regardless of stellar flux. The methods guiding our search are logical extensions of Earth's example, yet they reflect only one path life has taken. As detection techniques advance, broadening criteria may reveal environments that do not mirror our planet but still offer stable chemical niches. Expanding perspective does not abandon carbon or water. It recognizes that life, if it exists elsewhere, may adapt to conditions that appear unfamiliar from the vantage of a single world. For centuries, the night sky suggested isolation. The stars appeared distant and unreachable, fixed points scattered across a dark expanse. Philosophers and astronomers alike debated whether Earth was singular or simply the only world known to us. Without evidence of other planets, speculation lingered at the edge of imagination, unanchored by data. The shift began quietly, not with a single revelation, but with accumulating detections. Each confirmed exoplanet carried weight beyond its mass and orbit. Together, they altered a long-standing assumption. Earth was no longer the sole confirmed example of a planet. It became one entry in a growing catalog, one configuration among many. The realization did not diminish its significance, yet it repositioned it within a broader context. Seeing Earth as one data point reframes long-held narratives. The processes that shaped continents, oceans, and atmospheres are not unique events, but outcomes of physical laws operating throughout the galaxy. Planet formation, once understood only through our solar system, now appears as a common consequence of star birth. This continuity between distant systems and our own fosters a sense of connection rooted in shared physics. The psychological impact extends beyond astronomy. When Earth stands alone, its history can feel singular, even exceptional. When similar-sized planets orbit other stars, the possibility arises that familiar conditions may recur elsewhere. This does not confirm the presence of life, yet it expands the conceptual space in which life might emerge. Humanity's place becomes both more modest and more expansive at once. Modest, because Earth is not structurally unique. Expansive, because the same universal forces that shaped our world operate on a galactic scale. Science itself has transformed in response. Astronomy, once focused primarily on stars and galaxies, now integrates planetary science as a central pillar. Disciplines intersect, drawing from atmospheric chemistry, geophysics, and biology to interpret faint signals. The search for exoplanets has shifted from curiosity to precision, guiding the design of telescopes and missions specifically engineered to probe atmospheres and surface conditions. Entire research programs now explore habitability as a measurable property rather than a philosophical question. Public imagination has followed this change. Conversations about distant worlds no longer rely solely on fiction. They rest upon confirmed observations. Even without images of their surfaces, these planets possess measured radii, densities, and orbital periods. Their existence narrows the conceptual gap between speculation and evidence. Within this evolving landscape, Earth remains the only world known to host life. Yet it is no longer framed as an isolated anomaly. It occupies a broader continuum of planetary diversity, its characteristics echoed in distant systems. The recognition that we share the galaxy with countless other worlds has reshaped perspective, embedding humanity within a cosmic context defined by abundance rather than solitude. Catalogs may list promising candidates, yet every entry remains an outline drawn from distant light. We infer radius from dimming starlight, estimate mass from subtle gravitational shifts, and model temperature from orbital distance. What lies on the ground of these worlds, however, remains concealed. No telescope today can resolve continents, oceans, or mountain ranges on a temperate planet orbiting another star. Surface composition, weather patterns, and geological activity are reconstructed through theory rather than seen directly. Even when atmospheric gases are detected, their meaning is layered with uncertainty. Water vapor suggests the possibility of clouds or steam, yet it does not confirm open seas. Carbon dioxide may indicate greenhouse warming, yet the extent of that warming depends on pressure and circulation. Oxygen, often cited as a promising indicator, can arise through non biological processes under certain conditions. None of these signatures, taken alone, demonstrates breathable air at the surface. The chemistry we glimpse from afar provides hints, not guarantees. Distance reinforces this separation. The nearest potentially habitable exoplanets lie years away at the speed of light, and current spacecraft would require tens of thousands of years to traverse such spans. No probe has crossed even a small fraction of the gap between stars. Without physical sampling or direct imaging at fine resolution, these planets remain remote concepts shaped by indirect measurement. Their landscapes, if landscapes exist, are known only through equations and simulations. Environmental risks compound the uncertainty. A planet within a temperate orbit may orbit a star prone to intense flares, subjecting its atmosphere to sustained radiation. Another may retain a dense atmosphere that drives surface pressures beyond what complex organisms could withstand. Tidal locking could create stark thermal gradients. High gravity could alter biological structures. Even slight deviations from Earth's balance of atmospheric composition, magnetic shielding, and geological regulation can shift conditions toward extremes. Earth's uniqueness, in this context, does not imply cosmic rarity, but confirmed familiarity. It is the only world whose biosphere has been observed in detail, whose oceans and clouds are directly measured, whose atmosphere sustains complex organisms. Every exoplanet candidate remains provisional, defined by probability rather than lived reality. The phrase Earth 2 suggests replication of all essential traits, yet no distant world has been shown to match our planet across size, orbit, atmospheric chemistry, surface water distribution, magnetic field strength, and long-term climate stability simultaneously. The search continues to narrow possibilities, refining parameters, and improving models. Still, the distinction persists between promising and proven. Among thousands of worlds, some may approach resemblance in certain respects, but none carries the comprehensive evidence that defines Earth as a living planet. For now, the title Earth 2 remains aspirational, awaiting observations that reach beyond inference into direct confirmation. The next half century will not unfold in silence. Instruments already planned and those still on drafting tables promise sharper vision, wider mirrors, and more sensitive detectors than any that came before. Space-based observatories will likely carry segmented mirrors spanning many meters, optimized to block starlight with extreme precision. On the ground, extremely large telescopes rising above desert horizons will gather light with apertures far exceeding those of earlier generations, refining measurements of distant planetary systems. With increased resolution and improved coronagraphs, direct imaging may shift from rare demonstration to routine practice for certain nearby stars. Instead of inferring a planet's existence solely through transits or stellar motion, astronomers may isolate the faint glow of reflected starlight or thermal emission from the planet itself. Such images would remain small points of light, yet they would allow detailed spectroscopy free from some of the geometric constraints that transit methods impose. Mapping brightness variations over an orbit could hint at cloud patterns or surface contrasts, offering indirect glimpses of planetary features. Atmospheric mapping will likely advance through high-precision spectroscopy across broader wavelength ranges. By resolving spectral lines with greater clarity, researchers may track how gases vary with longitude or season. Repeated observations could reveal shifts in cloud cover, temperature gradients, or circulation patterns. Instruments tuned to infrared and visible wavelengths might detect combinations of oxygen, methane, carbon dioxide, and water vapor with increasing confidence, narrowing uncertainties that today blur interpretation. The strength of biosignature evidence will depend not on a single molecule but on chemical context. Future models will integrate planetary geology, stellar radiation, and atmospheric chemistry to test whether detected gases can coexist without biological replenishment. If a planet exhibits sustained chemical disequilibrium that resists abiotic explanation, the case for life strengthens. Improved understanding of false positives will sharpen criteria, distinguishing between photochemical byproducts and metabolic activity. Advances in interferometry may further enhance sensitivity, linking multiple telescopes to simulate a larger aperture. Such techniques could increase contrast between star and planet, enabling detection of smaller, cooler worlds. Over decades, incremental improvements accumulate, reducing noise, refining calibration, and expanding sample sizes. Statistical confidence in atmospheric trends will grow alongside the catalog itself. Within this progression lies the possibility of identifying compelling, multifaceted biosignatures. Confirmation will require independent measurements, repeated over time, and consistent with theoretical expectations. The first such detection, if it arrives, will not erase uncertainty entirely, yet it would mark a transition from plausible habitability to probable biology. The coming decades will extend our reach without closing the vast distances between stars. Through enhanced optics and refined analysis, the light arriving from distant systems will carry more information than before. Each improvement transforms faint signals into structured evidence, gradually clarifying whether any of those remote points harbor processes comparable to life. Across the span of the Milky Way, thousands of planets have moved from hypothesis to measured fact. Each carries an orbit traced in data, a radius defined by light curves, a mass inferred from motion. The catalog grows steadily, filling with super-Earths, gas giants, compact systems around red dwarfs, and temperate candidates circling quieter stars. The galaxy that once seemed sparsely populated with worlds now appears abundant, structured by planetary systems as diverse as the stars themselves. Within that abundance, only a small fraction rests within conditions considered potentially habitable. Fewer still resemble Earth in size and stellar environment. These rare alignments, where distance, mass, and atmospheric retention may converge, are scattered across light years of space. They are real in the sense that they alter starlight in measurable ways, yet their surfaces remain unseen, their climates reconstructed through models rather than visited or photographed at close range. Distance remains an unyielding boundary. Even the nearest promising worlds lie beyond practical travel with existing technology. Generations would pass before a spacecraft moving at current speeds could approach them. For now, exploration proceeds through photons alone, signals collected by mirrors and sensors, translated into spectra and probabilities. The gap between detection and visitation defines our present era of discovery. Amid this expansion of knowledge, one fact remains steady. Earth is the only planet confirmed to host life. Its oceans, forests, and atmosphere are not theoretical constructs but directly observed systems. Every other candidate stands within a gradient of possibility, supported by inference and constrained by uncertainty. The recognition of countless worlds has not diminished this distinction. Instead, it has sharpened awareness of the delicate alignment that sustains life here. The search continues, because each improvement in instrumentation reveals deeper nuance. New telescopes refine atmospheric measurements, expand statistical samples, and test models against observation. With time, signals will grow clearer, false positives fewer, interpretations more robust. The process advances patiently, grounded in measurement rather than assumption. The universe, as it unfolds through data, is not empty. Planets form readily, and some occupy temperate orbits. Yet welcome implies familiarity and accessibility, qualities not yet demonstrated beyond our own world. The cosmos offers variety and scale, but confirmation of living landscapes elsewhere remains incomplete. Within this quiet reality, perspective settles. We have found possibilities, but for now, home remains rare.